This is the fourth lecture in a series of lectures on special relativity with emphasis on a more mathematical approach. This particular lecture is on momentum and energy in special relativity, in particular, how it's viewed from a non-variational formulation. I'll parse this lecture out into three components. First, we'll define momentum, a three momentum in three space without any variational principles using a couple of axioms, and we'll show you how you can get the correct relativistic three momentum. Then I will show a more general and widely accepted approach using Minkowski four momentum. And lastly, we will see that a certain axiom will help us derive something called an energy dispersion relation, which relates energy to momentum. First, relativistic three momentum. So this is three components, and what we'd like to do, the axioms here are defined in such a way as to create a definition for relativistic momentum that looks and acts like classical momentum. First of all, this first axiom basically says that we expect whatever the momentum is, it should be parallel to the velocity vector. We don't know how much bigger it is, and we'll broadly interpret this to mean as some mass times the velocity in three velocity. Whatever this function m of v is, and at this point we don't know what it is, but whatever it is, we should pick it so that three momentum is conserved. That is to say, very precisely, that suppose in some frame k we have, in here I've got a sum of momenta prior to a collision is equal to its sum of momentum after the collision. So this is something we can see in one frame k. So if we assume that this expression is true, namely that there is a conservation of momentum in frame k, then we expect whatever the definition of momentum is, that it should also be conserved within the frame k prime. And we know how to get vectors from vectors in k and translate them into k prime, but more on that later. The advantage to using this approach is that it doesn't require variational mechanics, and the disadvantage is that it's a lot more complicated. It also has this function m of v, and it's typically in the derivation one considers this to be the mass that's dependent on the speed of the object. But the more modern approach is that there is no change in mass, actually, only that the mass m naught, the rest mass m naught, is invariant between frames, and m of v is just some function. So how does one take these axioms and derive this function m of v? Well, okay, so this is taken out of a reference number 2, which I'll point out at the end. We're going to consider an elastic collision between two identical particles. Blue here indicates the speeds or the velocities of the particles before the collision, and red indicates the velocity of the particles after collision. In this left-hand picture, this is what's observed in frame K. On the right, this is what is observed in K prime. Let's go back to K. So I have a particle here coming in, particle A, with a certain velocity, and it hits the particle B coming in at the origin, and then they bounce off each other, maintaining an elastic collision, and they go off in different directions. And there's this angle theta here with respect to this axis after this collision. And just so you know this, so the masses are equal. So whenever I draw one of these things, these could equivalently be momenta vectors, because you're going to multiply it by the same constant. So let's say that this is what we see in K. What we're going to do is we're going to do a little trick here. Is we're going to say, let's not pick just any old reference frame K prime that's moving. We're going to pick an inertial frame moving K prime that's moving in the direction of the one component of the A velocity. So what that means is that that's the one component is in this drawing here on the left, that's this X component. So that's V1A. And after the collision, because it's elliptic, it's V1A in this direction as well. So if I was moving at this speed, this velocity, and I saw this picture, what one would see would be, you would see this particle coming down. It gets hit and then it goes back up this way, but it would be vertical in this reference frame. Okay, so what does this look like? Well, it's a real mess. You can look in Classical Mechanics by Greenwood, and if you have these identical spheres that are colliding, and you look at that picture, then I have you can compute using the speed and the cosine of the angle, or the speed and the sine of the angle. You can compute the x, y, and z components of these velocities. And here, bar means after the collision, no bar means prior to the collision. So for example, VA is the velocity of particle A before the collision, and then after the collision, it's V bar A. I can write that down for VB and V bar B as well. And it's just doing a little trigonometry, you can find out what all these components look like. Now, if you use the frame K prime with this very particular velocity, so this velocity here of between the frames is the same as the first component of VA and VA bar. So the elasticity assumption implies that this has got to be true. And what we know is that so VA prime is going to have a zero component in the x direction, and V bar A prime is going to have zero in the x direction. So in the other frame K prime, what they see is just the y components of these velocities and their opposite signs. So then you can do the same for VB. If I knew what the angle after in frame K prime was, then I could figure out what the x and y components of each of these velocities were before and after collisions. So that's good. Now, what has to be true is, so what you can do is you can compute. I don't know. So what do I know? What do I know and what do I not know? I know V. I know the angle theta. And from these expressions above, I can use the velocity formulas I derived before to figure out what these velocities K prime must be in the K prime reference frame. So I'm going to use the three velocity conversion formulas, and that's going to be a lot of algebra. And I'm going to find formulas for the three unknowns in K prime. That is the certain components of the velocities and the angle. And I don't know those. What they do in this reference 2 above by Greenwood is they basically say, look, this has got it. Once I've done all that, I know what the pictures look like and I know how the velocities add. So if I use small angle approximations, I can find out a necessary condition for the function m of v when I put everything together. So if I do that, there's a lot of algebra and a little bit of calculus, but if you go through all of that, and I urge you to look at the reference, you can derive this function m of v. In other words, momentum can only be conserved if m of v is this very particular function. And so that's how it's rough. That's a rough outline. We're not going to dwell on this, but this is a rough outline of how one goes about defining a three momentum that's relativistic, that preserves conservation of momentum. Let's go to the more modern approach. More modern approach is to use something called relativistic four momentum. Well, we had three velocities and we have four velocities. So just in a very, very parallel manner, we'll have three momenta and we'll have four momenta. Four momenta is going to be defined to be a momentum in four spacetime. In particular, in Minkowski spacetime. And it has the very obvious definition that the four momentum p is the rest mass times the four velocity u. So that is to say that it's m naught, some constant in any reference frame, times this derivative of the Minkowski coordinate with respect to proper time. So for momentum, if you just do this calculation, you get that it's got the first component associated with the time component, and then it's got the regular momentum little p sitting in there. For this definition, you can prove that the magnitude of the momentum in frame K is the magnitude of the momentum in K prime. And by that I mean the Minkowski norm and Minkowski norm. And when you do that calculation in either frame, it turns out to be m naught times c. So we get everywhere the magnitude of the four momentum is a constant in any reference frame. Let's see this proof. It really goes along. It's almost identical to the proof for constancy of the invariance of the magnitude of the four momentum. The proof for that, and this is almost exactly the same. So basically what you do is you start with the four momentum definition. You go from proper time tau to regular time t, and you get this four vector. First one being time, the next three being the spatial coordinates. You write down what those velocities are in t, and you look at each term and you say, well, this can be parsed out into one component in time and a three component momenta vector p in just the last three spatial coordinates. So then you take this last expression, you say, look at this vector here, this one right here, and I'm going to take the Minkowski norm squared. So that's this thing squared minus the regular Euclidean of that thing squared. So that turns out to be this expression here, which a little bit of algebra simplifies to m naught squared c squared. So you take square root of both sides, and you say, okay, that means that the momentum in four momentum has got a magnitude of m naught c. So it's constant. It's an invariant. So then in K prime, if I take any other frame, I want to prove that under the Lorentz transformation, this is still true. So what we we want to translate and look at the form momentum in the other reference frame, K prime. Well, that's ds, the Minkowski prime coordinate with respect to proper time. And again, you get this Lorentz matrix times the Minkowski coordinate in K. This Lorentz matrix, because the frames are inertial, it's a constant matrix and it can be pulled out. You group these two things together like this, and the second term is just the form momentum in K. So this says the form momentum in K prime is the Lorentz matrix times the form momentum in K. I already know what the length is of this thing here, and by the previous invariance theorem, if I have two 4 vectors related in this manner, their lengths in the Minkowski norm have got to be the same. So that's a proof of this invariance of this thing in any reference frame. The next thing that's typically done is an assumption has to be placed somewhere relating momentum and energy. And there's a rationale, which I'll point out after the fact. But the assumption that's made is that the first component of the form momentum is actually equal to the total energy divided by c. Where does this come from? Well, it's not obvious where this would come from. But let's, for the moment, suppose that this axiom here is true. What can we then say? Well, if the first component of the form momentum is actually now E over C, then I know that this vector has got a fixed magnitude. Namely, if I take this expression here, this last one here, it's got one component and then a 3 vector here below with V. It says the length of this thing has got to be equal to the value that we've just found, namely m naught c. Well, given this form, that's just this thing squared minus this thing squared. And now what I've got is I've got an equation. I've got this is equal to another expression on this side. Well, what I'm going to do is I'm going to solve that equation for E. And if you solve this for E, you get an expression for the total energy, which has got this factor gamma in it. And when the velocity is at rest, gamma is 1, so you get E naught is equal to m naught c squared. So to recap, this is what happens. If you assume the first component of the form momentum is this, then you get a formula for the energy that's a consequence of the fact that the form momentum is invariant in reference frames. And once you have the total energy for any velocity, you can figure out what it is for velocity 0, and that's Einstein's E equals mc squared. So all of this hinges upon this axiom here, which we have no rationale for. There's absolutely no rationale for this right just yet. So let's see if we can do something about that. So if you do that, we know that if we make that assumption, we get this expression for the energy. It's this thing here. And if I put in that gamma factor, it's this square root of 1 minus v squared over c squared on the bottom. Well, we hope that this expression is true when the velocities are low. So in particular, what I want to do is this has got a v over c in here. This is beta squared right here. That's the non-dimensional velocity squared, beta squared. And I can create basically a Taylor series expansion in beta. So I do a Taylor series expansion of this thing in beta. So that means that E will equal this Taylor series expansion for small beta, or when V is not close to C at all. And it has a leading term in blue, and then a correction term to the order of beta the fourth, plus other correction terms. That means that the total energy, according to this formula, is necessarily this blue expression at low velocities. And if you look at that expression, the leading term is the rest energy, and the next term is the classical kinetic energy. So what this proves is that if I make the assumption that P naught is E over C, I get a low velocity energy that is consistent with classical kinetic energy. However, E is now no longer just the kinetic energy at rest. It has a rest energy, and it has a kinetic energy. All these other terms are corrections to the relativistic corrections to the kinetic energy. So how do you have to define relativistic kinetic energy? Basically, you take the total energy and you subtract the rest energy, and what's left over must be kinetic. So we get this new expression, which is no longer looks like the classical 1/2 mv squared thing. It's got a gamma in here and a -1. So to make everything consistent with this assumption, I have to define kinetic energy to be this expression. And then it agrees with the limit beta going to 0. Okay, one last thing here is that if you want to show that if I have 4 momenta that's conserved, that will actually imply 3 momenta is conserved. And if I can show that, then that will validate the definition of P further, namely that, our 4-dimensional, let's go with it here. So if I want to prove that if the sum of momenta, say I've got a whole bunch of particles in here and I'm adding up these momenta, and let's say that their total momenta of the system is some total momentum that's fixed. So this sum of all the momenta is equal to some constant momentum. Then I claim that in the K prime frame, I see something similar. I see that if the conservation holds in K, then there will be a corresponding conservation law in K prime. The only difference is that the total momentum will be a little bit different. It'll basically be the K total momentum times the Lorentz matrix will give me the K prime total momentum. And this is very, very easy to see down below. You start with K prime momentum, and it's just a consequence, again, of when you take these derivatives and you're transforming one momentum to the other, this Lorentz matrix sitting in here is always constant, so I can pull it out. So I pull it out in my group terms, and I get pk prime is lambda pk, and that's got to be true for every k. So I add them all up, and I get the sum in the k primes momenta is equal to lambda times the sum in the k's, and therefore proving this result. So in summary, outside of not having a great rationalization for what that first P naught term is in terms of energy, if we do make that one assumption, then 3 things happen. 1, you get the correct relativistic momenta, 3 momenta, and then you get an energy relation between energy and momenta that yields E equals mc squared when the particle's not moving. And furthermore, if I use that 4 momenta definition, then 4 momenta, if it's conserved in one frame, it's conserved in the other frame. And because the 4 momenta is conserved, the 3 momenta must be as well. That ends this